Alright, so in this video, we're going to talk about the next part of the lab procedure, and that's the separation of the biodiesel. So at this moment, what's happened is that you've went through a few really hard, difficult, laborious days making the biodiesel. Whoo! Gosh, I was here forever, and it was such hard work. So what's happening now is that this biodiesel has been formed, and you're probably going to see two layers in your flask when you go back to it when it's ready. So the separation is going to have to take place. Number 9 says the separation in the mixture should be present. If you only have one layer at this moment, folks, it is over. You might as well pack it up and go home and quit for the semester, because this lab is going to have to be restarted all over, and that's going to require more and more days. And if you're unlucky and you didn't schedule it the right way or plan it the right way, you might just not simply have enough time anymore to do the biodiesel lab. So the separation, it has to be separated from something, and that means two layers should be formed at this moment in time. Number 10, a third layer could also be present. If you see this, do not freak out. That is perfectly okay. When you begin to start the separation and the washing, what will happen is that that third layer will often disappear. So it will get washed out in the end. Don't freak out about it, but you at least want two or more layers at the separation stage. Number 11, the glycerin that was cleaved from the triglyceride. So keep in mind, the glycerin is going to be the product that we talked about up here. So this is the 3-carbon chain with the OH groups. I want you to look at these OH groups. These OH groups are very polar, and there's 3 of them. So there's some polarity that's going to be assigned here with these multiple alcohol groups that are on glycerin or glycerol. On the ester side of the house, though, not so much. The ester side of the house, we've got some free pairs of electrons. There's 2 sets of electrons on this oxygen, and we also have 2 sets of electrons here on that oxygen as well of the ester. But the thing here is that, yeah, that does make it negative or slightly negative. Yeah, there's a little bit of polarity that's assigned here because those free pairs of electrons exist. But the issue with this one is that this R group, and then this R group, they're big and bulky. They could be, at least. And that big and bulky area of the compound will actually cover up, in a way, those free pairs of electrons and those charges. Not fully, but they do help cover it up so it's not as polar. So what I'm trying to say here is that the glycerin, because of these exposed alcohol groups, and because they are polar, because each oxygen has a free set of electrons on them, which makes them all polar, because that is there, this polar type of molecule is going to be more water soluble, and then the organic-y piece, which is the biodiesel, will not be as water soluble. So hence we get 2 different layers. That happens here. So number 11, the glycerin that was cleaved from the triglyceride is denser and darker than the biodiesel, and it will separate and go to the bottom of the flask or eventually into the separatory funnel. So what you're seeing here in diagram number 12 is when you pour this solution into a separatory funnel, you are going to disturb it yet again. All right, that's going to be a thing. That's okay, whatever. We're going to disturb it, but it doesn't take as long to separate here. About 30 minutes, give or take a little bit. So number 12, it says when you pour this solution into a separatory funnel, you'll see something that looks like this. So your biodiesel is going to be on the top. That will be yellowish golden color. And then your glycerin is going to be down here at the bottom. That glycerin is going to be much darker. It will be an amber color or dark brown color most of the time. And because it is more dense, it settles to the bottom. These 2 layers do not mix, so they're immiscible. So the top layer is more non-polar, and the bottom layer, the glycerin, is more polar, so they don't mix and they separate. And we're going to drain that off, and we're going to set it to the side. We don't need that glycerin for anything. Now, we could be creative, and we could do labs using that glycerin for other purposes. We're just not, but we could if we wanted. But the biodiesel on top is what we're after this time. Number 13, it says, pour the crude into the separatory funnel. Allow 30 minutes to separate. So you want nice, clean layers here. That's the whole objective. We want to separate these two things. We want to separate them as much as possible. So for that reason, give it some time and let it separate. Number 14, drain the glycerin from the biodiesel. Number 15, using a spray nozzle from a spray bottle. Gently, and gently, okay? Gently spray the water onto the surface of that biodiesel. You want a mist of water to settle on the top of that biodiesel, and you want it to slowly go through the biodiesel in order to grab all of those contaminants and components that don't need to be there and drag them slowly to the bottom of the separatory funnel, because that's where the water is going to go. The biodiesel, has a density less than 1. So because of that, water, which close, 1, but not quite, but close, settles to the bottom, and yet again they are immiscible, and that's why this happens. So the water is going to grab all of your salts that are left over. It's going to grab all of maybe the alcohol that's left over. It's going to grab anything that is water soluble, drag it through the biodiesel. So it's going to get disturbed a little bit. It's going to go cloudy a little bit here in the beginning, and that's okay, but it's dragging all of those impurities out of your biodiesel to give you a cleaner product. So number 16, water will trickle. It will remove all of the contaminants, and the water layer could be cloudy, and if so, that's fine, not a big deal. Number 17, if the force of the water is too great, it could hydrolyze the free fatty acids, which will then combine with the base, because there's probably going to be some left over, to make soap, and that will never go away. So what you'll end up here with is a soap product and not a biodiesel product. And that is why this is very important to go gentle in the very beginning of the process. Once we get a lot of the base out, then we don't really have to worry about that stuff anymore. But in the beginning, patience and slow is going to be better. After we wash it once or twice, we start to see that water layer not get cloudy anymore. Then we can actually add water at a quicker rate and clean it faster, because we're not worried about the reaction that happens between the base and the biodiesel anymore, because the base is not actually there. Number 18, drain the water layer. Number 19, it says repeat that washing until that water goes clear. Number 20, it says the biodiesel could have gotten cloudy at this moment. And the reason is because there could be a little bit of water that is getting trapped inside of the biodiesel layer, and we need to get rid of that. So that is residual water that's left over, and that's very simple to get rid of. The only thing that we have to do is put it on the hot plate. Number 21, it says turn a stirrer on until a very strong vortex forms. So we really do want this to be wide open. I mean, we want that stuff to be spinning as fast as it can spin. But then it says ensure that the temperature does not go over 110 degrees. So we are above the boiling point of water, just slightly, but we're above the boiling point of water, and that's really what we're after here. 22, as the biodiesel heats, the stir bar will help drive off any remaining water that's in the lower depths of the biodiesel layer. So that vortex is really just going to increase the exposure of the water, so that way that water can evaporate quickly and leave quickly, and we don't have to leave the biodiesel on heat for a long period of time. That biodiesel should eventually go clear. That is what you're after here. So almost like what it looked like in the very beginning is what you want to look at here. It's going to be a very clear product. You can see through it. It will still be colored. There'll still be a light yellowish color tinge to it, but clear means you can see through it. 23, once no visible water bubbles or droplets are present, turn down the stir plate. Allow the sample to heat slowly on a very slow stir for 1 hour. So this is going to help drive off any of the residual water that is actually there in the last stages of the heating process. Number 24, check your temperature. Make sure you don't go over 110. And 25, once the biodiesel clears, set the sample aside for 1 day. And it's best to fully cool the sample to drive off any water before you go through with any other test. All right, so now let's take a look at this. Here's a 1-day sit. So if I go back to the production, it looks like I need to heat this for a day, Then I need to let it sit for 2 to 3 days. So that's a possible of 4 days here. Then in the separation stage, I'm going to be able to do that on 1 day. But then after I get to the final stages of the separation, I'm going to have to let it hang out for another entire day. So now we are possibly 5 days into this laboratory experiment. Again, do other things while you're working on this. You have to in order to get these labs finished. Next up are all of the tests that come along with the biodiesel product that you have now made. And there's a number of them. So like I said in the very beginning of this live video, it's a whole lot of box here of biodiesel tests. And most of these biodiesel tests are going to be coming from ASTM. ASTM is going to be the group that is going to be in charge of making these procedures that are tested, that are recognized, and that really are only approved for the biodiesel testing of this type of product. And what we're after here is something that is going to be close to a B100. Now, what's the tests are going to do, they're going to give you threshold values. This threshold value does not necessarily mean B100, but it means pretty darn close to B100. So you might not be 100% biodiesel, but you're going to be 98, 99% biodiesel at least. So if you are trying to produce this, and if you're trying to sell it as a biodiesel source that is pure, and that you've tested it to make sure that it's pure, these are just some of the tests, not all of them, but these are just some of the tests that you can do in order to prove that concentration that you've made and the purity that you've made. All right, so the very first one is ASTM D2709. And D2709 is a water test. And this water test is going to be done with a Karl Fischer titrator, KFT. So if you've taken 115 or if you've taken 114, you've been exposed to our Karl Fischer titrators, maybe more than once, of course, right? And we're going to yet again use those KFTs in order to calculate the water percent that is going to be included in my sample. Now, the issue here is that this water percentage should be very low. This very low water percent means that hardly any water is present, and it should be straight up biodiesel at this moment. But that's okay, because Karl Fischer is built in order to do very low concentrations. And what we have in our laboratory is suitable enough. We don't need anything else other than what we already have. A traditional Karl Fischer titrator can easily go down to 0.05%, and that's really what we're after here. So Karl Fischer titrators, just as a quick review, that is specifically for water. This is not a moisture test. This is an actual water test. I am really determining the amount of exact water that is associated in that sample and not moisture. Moisture is water plus all the other things that can evaporate, but water is water, and that's what KFT is all about, and that's how it's built. All right. So sodium tartrate is going to be used as the standard that we're going to have to use first before we go through the titration of our samples. Keep in mind that the titrant that we use is actually not shelf stable. And because of that, this titrant has to be restandardized every single time that it's used, day after day after day. So sodium tartrate will allow us to accomplish this. So in the directions, it's going to tell us to measure out sodium tartrate, and we're going to do this 3 times to get a nice average. So I'm going to measure out a certain amount of sodium tartrate, about 0.2 grams of solid, give or take a little bit, doesn't have to be exact. So just about run of the mill. And we're going to add that to our Karl Fischer titrator, and then we are going to titrate that sample under the standardization method. We need to standardize the titrant, so the standardization method will be included in those titrators. So make sure that you're operating under the right method, and if you need help with that, of course, come and get me or come and get someone else that's helping out in the lab. Doesn't really matter, right? We're there to help you and to double check, especially when these types of things are concerned. So the sample is going to get titrated, and on the computer screen, you are going to see a concentration that's going to be provided. That concentration is going to go here, and that concentration will be in terms of milligram per milliliter. That is how we regard the standardization, and it makes our math a little bit easier later after the fact, but that is the proper concentration, and that's also what shows up on the computer screen. You just simply need to write it down. Next, we're going to do it again, another 0.2 mils, titrate, and then we do it for a third time, another 0.2 grams, and then we titrate that as well. All right, so once we titrate those standards 3 times, then we're going to take a nice little average of these, and that average is going to go here for our concentration. All right, so that is 1/2 of the Carl Fisher titration method that we need to follow. What happens next is that after we get the average of the titrant, we have to enter this in to the KFT titrator. And the reason is because the instrument doesn't know. The instrument has told you a number and it has told you a value, but it doesn't do anything with those values on its end. That it relies on you to do that. That's why we're users of that piece of equipment. So once I titrate 3 times and get an average concentration, then I am going to be responsible to go in, or you going to have to go in and key that concentration into the instrument, so that way it knows what to use from this moment on. Otherwise, it does not know that. So again, if you need steps on how to do that the proper way, you come and get me or come and get someone else, and we will walk you through those steps. It is not a big deal. It's not an issue. I do it all the time, so don't feel bad if you need some help with that. All right. Next up, we need to now titrate the samples. And up here at the top, after we enter the average into the KF titrator, then we're going to titrate the samples, and we need about 0.8 to 1 milliliters of the sample. So this is a liquid sample, and keep in mind the proper way to inject liquids on a Carl Fisher titrator. So we use the syringes and we use the needle tips. So we will suck up the biodiesel into the syringe, and then what will happen is that we'll puncture the septum of the instrument and we'll squirt in about 0.8 to 1 milliliters of sample. Use the guide on the needle to kind of determine that, but keep in mind that this, just like sodium tartrate, is going to be in reference to grams. So on the syringe, you squirt until you get a total of about 1 mil that has been delivered. And then you still need the balances, right? So you need the mass beforehand, and then you need the mass after. And we're going to key the mass of the sample in, not the volume of the sample in. All right, so this is no changes versus what we saw in 114 and 115. After we do that, we'll do it a second time, we'll do it a third time, and then we'll get a nice average here of the concentration in terms of percentage. And then finally, does the sample pass the accepted value? So the accepted value, once again, is less than 0.05%. If it does not pass, there is a chance that you didn't drive off all the water that you needed to, and longer heating periods or, a reheat to drive off that extra liquid could also be a possibility in order to get that percentage way, way lower. So if this does fail, that's okay. Just circle yes or no. But if you were required to try to get B100 as much as possible, then you would just do another heat period or another kind of let it hang out warm period, or place it in the oven, so that way that water can go lower and lower and lower and lower. Next up, another test that we're going to do using equipment is going to be our density meter. And the density meter is going to be used to report the density and the specific gravity of the biodiesel that you have made. Nothing really that I have to talk about here as well. The density meter you've used already probably this semester. You also used it in probably 114 and 115 both. You know how this thing works, and its job is to give you the density of the solution that you are using. There's no calibration that's going to be needed either for the instrument. We're going to assume that it's working the right way. So literally inject the sample into the instrument. You want to make sure that there are no air bubbles that are happening on the inside of that display. Air bubbles are always bad. It takes up volume. If volume is taken up, that's less mass that's not there, and you get an incorrect density and an incorrect specific gravity because of that. At the end of this, though, what I do need to really stress here is the cleaning aspect of the density meter. This is an oil, okay? And that oil is very organic-y. And this can gunk up our density meter very quickly if you are not very careful. So anything at all that you want to pay attention to with the density meter is the cleaning step. And number one, we're going to use a bunch of methanol to clean out that chamber. Methanol is used in the reaction. Methanol was almost a reactant, of course, for the reaction, but it makes a great solvent. So methanol is going to be pushed through, and it's going to help dissolve any gunk that might be left over in that U-tube chamber of the density meter. Then we're going to follow that by water flushes. 2 or 3 flushes of water in those syringes. I mean, just one after another, after another, after another. You can't use too much water. And then finally, we're going to follow that by acetone. And that acetone is going to help drive the water out. So it evaporates quickly. Again, it makes a great solvent. It might be able to capture stuff that water and methanol didn't get a hold of. But once more, 2 or 3 syringefuls of acetone need to be pumped through the instrument. So keep it clean, so that way someone else that needs to use it will not get a gunked up U-tube that will be almost impossible to clean out and use. And that will mess up their data, and they'll be very angry, and I'll be very angry because of it. So the data sheet's going to ask you for the density, which will be on the report, as well as the specific gravity on the report. Do not use a pycnometer. It says in the directions you can use a pycnometer if you want, but this is like a last resort. So if our density meter is kerplunk, then we use a pycnometer and we can get the same type of data here without an issue. Next up is the temperature of the measurement. So 20 or 25 degrees, whatever you choose, just make sure that you put that down. We are reporting specific gravity, so everything is in reference to each other. So if you measure water at 20, the oil needs to be at 20. If you measure water at 25, the oil is going to be at 25. That temperature key-in value is what the density meter is going to be using in order to calculate specific gravity. So for the most part, density or specific gravity is 20 to 25, 20 or 25. It doesn't really matter. You'll get a good enough value here. If it was me, I would key this in at 25 degrees and run it. Your accepted value here is 0.88. So notice it doesn't give you a window. It just says 0.88 for the biodiesel. So yet again, does it pass the ASTM accepted value? Yes or no? And then with that said, we move on to the next part of the lab procedure. All right. The next part of the lab procedure is a viscosity reading. And this is probably something new that you've not done before in any of our labs. If you did, it might be in 114, which is wet laboratory. But this is a property like density or melting point or boiling point that we can measure with liquids. And we need a specialized instrument, or we need a piece of glassware in order to make the viscosity reading happen. So I need to talk a little bit about what this viscosity test is going to require and the motions of going through the proper way to use these pieces of glassware in our lab facility. So that's going to be in the next video. We're going to pick up with viscosity ASTM D445. So come back and see me, and we'll go through the motions of talking about what this test is going to include.